Hello, I'm James, and I'm going to be discussing the solution to the step question on assignment 14 of the foundation modules. So this is a question about the Fibonacci sequence. This sequence does seem to come up a fair amount in STEP. I know there's definitely a question on the later modules where you have to prove some properties about the Fibonacci sequence. This is slightly different. This is actually finding an explicit form for the terms of the Fibonacci sequence. Okay. Now, this question, in my opinion, is quite difficult. There's a lot of algebra for the first two parts, and then you have to use quite a clever trick for the last part. So this is a fairly difficult question. Hopefully, I explain the thought processes well enough here. Okay, so what does the question say? It says the first four terms of a sequence are given by, so the first term is 0, then it's 1, then it's 1, then it's 2, and we're told that the general term has this form, okay, where a, b, lambda, and mu are independent of n, and importantly, a is positive, okay? That will allow us to get a specific value for sort of a, b, lambda, and mu. The first part of the question says, show that this formula holds, and find the values of our four unknowns here. Okay, so how would we do that? Well, all we really know is what these values are, so I would just substitute them in. That's effectively what I would do. So what do we know? So we know that f0 equals 0, so substituting that into our general form gives us that 0 equals a plus b, right? Because lambda to the 0 is 1, mu to the 0 is 1, so we get 0 as a plus b, or in other words, a equals minus b. Okay? Let's now substitute in the other conditions. So f1 equals 1 tells us that 1 equals a times lambda plus b times mu. But since b equals minus a, you can write this as 1 equals a into lambda minus mu. Okay? Simply using the condition that we found from the first equation. Using the condition that f2 equals 1 gives us that 1 equals a lambda squared plus b mu squared. Similar to last time, this can be written as 1 equals a times lambda squared minus mu squared, using the condition that a equals minus b. And this can actually be factorized, so we get 1 equals a times lambda plus mu times lambda minus mu. Okay. And then lastly, we can use the condition that f3 equals 2, and we end up with that 2 equals a lambda cubed plus b mu cubed, or in other words, 2 equals a times lambda cubed minus mu cubed. Now, most people are familiar with this difference of two squares formula. There is also a difference of two cubes formula. There's also a sum of two cubes formula as well. This is a formula that I would recommend that you just learn. So the difference of two cubes, so lambda cubed minus mu cubed, is given as lambda minus mu times lambda squared plus mu lambda plus mu squared. Okay? You can check that this factorization works just by expanding out the brackets, but that is the difference of two cubes formula. Okay, how does this help us answer our question? Well, we want to show that this thing equals 2. Well, that's quite nice. We've already got this expression sort of in this term, right? So clearly we're going to be doing something with this, and we can combine this fact here with the last fact. So we know that lambda minus mu equals 1 over a. Substituting that in, we end up with 2 equals a times 1 over a, right, because lambda minus mu is 1 over a, times by lambda squared plus mu times lambda plus mu squared. The a and 1 over a cancel, and so we're just left with lambda squared plus mu times lambda plus mu squared equals 2, which is what we wanted to show, so as desired. Okay, cool. It now says find the values of lambda, mu, a, and b Well, we could use a similar trick on the second equation. So substituting in the fact that lambda minus mu is 1 over a, we end up with 1 equals a times lambda plus mu, and instead of lambda minus mu, we're going to write 1 over a. This gives us the equation that lambda plus mu equals 1. Okay. Well, now we have two equations, right? We've got two equations, we've got two unknowns. We can just solve this as a system of equations. So we can rewrite mu as 1 minus lambda, and then substitute that into this equation. So that gives us lambda squared plus 1 minus lambda times lambda plus 1 minus lambda all squared has to equal 2. Expanding the brackets, we end up with lambda squared plus lambda minus lambda squared plus 1 minus 2 lambda plus lambda squared equals 2. And so we're going to be left with a lambda squared minus lambda minus 1 equals 0, right? Okay, we can solve this using the quadratic formula. So in particular, lambda is going to equal 1 plus or minus the square root of 1 minus 4 times 1 times minus 1 all over 2 times 1, which is 1 plus or minus the square root of 5 over 2. Okay, so that's what we've got as our values for lambda. This is where we have to use the condition that a is positive, right? So since a is positive, 1 over a is positive, and so we need lambda minus mu to be positive. Now, by the symmetry of this equation, right? Okay, so basically we need to find our value of mu, right? We could substitute mu equals 1 minus lambda, and we'd end up with two values for mu. But it's actually a slightly quicker argument is to notice that this equation is symmetric in lambda and mu, right? We could have, the algebra is exactly the same as if we substituted lambda is 1 minus mu, right? You can exchange lambda and mu and it doesn't actually change the equation. What that means is it means that mu is also either 1 plus or minus the square root of 5 over 2. Okay? That's just by symmetry. If you're not too happy with that symmetry argument, you can, of course, just find mu explicitly by substituting into here. So we know that lambda is one of these, and mu will be the other one. Okay? Maybe I should have written this as minus plus, because it will be the one that lambda isn't. Okay? So if lambda was 1 plus root 5 over 2, mu would be 1 minus root 5 over 2. Okay? Cool. How do we determine which one's which? Well, that's where we're going to use this condition that since 1 over a has to be positive, we must have lambda bigger than mu, and hence lambda must be 1 plus root 5 over 2, and mu must be 1 minus root 5 over 2. Right? Because for a to be positive, we need lambda to be bigger than mu. Okay? Simple as that. Okay. How do we find a and b? Well, we have this formula here, right? We know that a equals, let's just move the paper up here. We know that a equals 1 over lambda minus mu. Well, what is lambda minus mu? Lambda minus mu, that's going to be 1 plus root 5 over 2 minus 1 minus root 5 over 2. This gives you 1 over 2 root 5 over 2, so let's just write that down. So it's 2 root 5 over 2, which is 1 over root 5. And b, if you remember from our very first equation, was just minus the value of a. And so b is minus 1 over root 5. Okay? And so our equation for the Fibonacci sequence is fn equals 1 over root 5 times by 1 plus root 5 over 2 to the power of n minus 1 over root 5 times 1 minus root 5 over 2 to the power of n. Okay? That's what the question was asking. Actually, it actually only asked you to find the values, but it's good to write down this equation explicitly. Okay, the next part of the question says using this formula, so using star is the equation, evaluate f6, that says. Okay, evaluate f6. So how would we do that? Well, let's write down the equation again on our new side of paper here. So we end up with, so fn was 1 over root 5, 1 plus root 5 over 2 to the power of n, minus 1 over root 5 times 1 plus root 5 over 2 to the power of n. Okay? Oh, that should be 1 minus. My mistake. Okay. So that's the general formula, and it says find f6. Well, that just involves substituting in n equals 6 into this equation. So that gives you 1 over root 5 times 1 plus root 5 over 2 to the power of 6 minus 1 over root 5, 1 minus root 5 over 2 to the power of 6. There isn't really a good way of evaluating this. We're just going to use the binomial expansion. You'll notice that a lot of things cancel out. So let's do a quick note. So 1 plus root 5 to the power of 6. We'll do this off to the side. So the binomial expansion says that this is, well, 1 to the power of 6 plus 6 times 1 to the power of 5 times root 5. Now at this point I forget the coefficients for, you know, I don't know what 6 choose 2 and 6 choose 3 are off the top of my head, to be honest. So it's very quick, just to, you know, draw out Pascal's triangle, just to work out the coefficients if you don't know them. If you do know them, that's perfectly good, but if you don't, then I always just draw out the triangle. So now I know that these are the coefficients that I'm going to be using. So I might have to go on to the next line, sorry. So 1 plus root 5 to the power of 6 equals 1 plus 6 root 5 plus 15 times root 5 squared, which is 5, plus 20 times root 5 cubed, which is 5 root 5, plus 15 times root 5 to the 4, which is 25, plus 6 times root 5 to the 5, which is 25 root 5, plus 1 times root 5 to the 6, which is 125. So that's what 1 plus root 5 to the 6 is. So f6 equals 1 over root 5 times by 1 plus root 5 to the 6 minus 1 minus root 5 to the 6 over 2 to the power of 6. So substituting this in, so we'll take out this 2 to the 6 as well. So it's 1 over 2 to the 6 root 5 times, so 1 plus root 5 to the 6, we've found an expression for that, so I'll just copy that in. And we'll notice that a lot of these terms are going to cancel when we substitute in 1 minus root 5 to the 6. So minus, I'm sort of running out of space, so I'm going to have to do it on the next line. This is minus, well, 1 minus root 5 to the power of 6. It's going to be the term's going to be the same, but we've got this minus sign, so they're going to alternate in sign. So the first one is going to be 1 minus 6 root 5 plus 15 times 5 minus 20 times 5 root 5 plus 15 times 25 minus 6 times 25 times root 5 plus 125. Okay, so that's the term. As I said, a lot of these are going to cancel. So 1 minus 1, that cancels. 6 root 5 minus 6 root 5, so we end up with a 12 root 5. 15 times 5 minus 15 root 5, 15 times 5, they cancel. 20 times 5 root 5 plus 20 times 5 root 5 is a 40 times 5 root 5. These terms cancel. We're going to end up with a 12, lots of 25 root 5, and then the 125s cancel as well. So that's the expression. Let's just try and simplify this. So we can cancel it out a little bit. So notice that all of these terms have got root 5 in it, so we can divide by root 5. All of these terms also have a factor of 4, so we can divide by 4, and so we'll be left with 1 over 2 to the 4 times by, so 12 root 5 divided by 4 root 5 is 3. This will be plus, so that'll be 10 times 5, which is 50, and this will be 3 times 25, which is 75. And so we're left with, so 75 plus 50 is 125, plus 3 is 128, 2 to the 4 is 16, 128 divided by 16 is 8. Okay, and so that is the value of f6. Okay, you might want to check this just by calculating the Fibonacci numbers explicitly and checking that f6 does actually give you 8, but that is the right answer. And then the last part of the question here says, evaluate the sum from 0 to infinity of fn over 2 to the n plus 1. Okay, so this seems like a bit of a weird question. Why are we suddenly dealing with infinite sums? Well, it turns out the result is quite nice. But the question is, how do we deal with infinite sums? Well, at this level, there are sort of two main ways to deal with infinite sums. Either it's going to be a telescoping series. So what that means is that there'll be sort of some positive terms, there'll be some negative terms, and they sort of all cancel out, possibly just leaving the sort of first and last term. Or we're going to have to use geometric series. They're the main two options when summing infinite series. So is this telescoping? No. All of these terms are positive. They are getting smaller, but they're not cancelling each other out. Is it geometric? Certainly could be. We could try and force it to be geometric. So let's see how we would do that. So we have the sum from n equals 0 to infinity of fn over 2 to the n plus 1. Well, we now know a formula for fn. Okay. Now what I'm going to do is I could write down this explicit formula for fn into our summation. The problem with that is that it's going to require me to write down this a lot of times. So instead what I'm going to do is I'm just going to substitute in this sort of more general form and then just substitute in our values for sort of a, b, lambda, and mu at the end. I think that's the easiest way of doing this. So what do we end up with? So we're going to end up with a lambda to the n minus a mu to the n over 2 to the n plus 1. Right? That was our general form. Remember, because b was equal to minus a. Okay, so that's our form for the sum. And like I said, our aim is to try and get this into geometric series. So let's try and split this sum up a little bit. I'm going to write it as a over 2 times the sum from 0 to infinity of lambda to the n over 2 to the n minus a over 2 times the sum from 0 to infinity of mu to the n over 2 to the n. The reason I've done this is because then we can write this as a over 2 times the sum from 0 to infinity of lambda over 2 to the power of n minus a over 2 times the sum from 0 to infinity of mu over 2 to the power of n. Okay, these are simply geometric series. They do converge. How do we know they converge? So lambda we showed was 1 plus root 5 over 2. That is, so lambda over 2 is less than 1. Is that something we need to prove? I would say we probably should prove that, that this is less than 1. So note that lambda over 2 is equal to 1 plus the square root of 5 over 4. So for this to be less than 1, multiplying both sides by 4, subtracting 1, we require root 5 to be less than 3, which is true. Right? So 1 plus root 5 over 4 is certainly less than 1, and so it can be summed as an infinite geometric series. And note that clearly 1 minus root 5 over 2 will be less than 1. Right? so that can also be summed. I guess you want to show it's bigger than minus 1, but that's a very similar argument to here. So what is this sum? So we end up with the sum from 0 to infinity of lambda over 2 to the n equals, so the sum of the geometric series is the first term over 1 minus the common ratio. The first term is when n equals 0, so that's just 1, over 1 minus the common ratio, which is lambda over 2. And so we're left with 2 over 2 minus lambda. Likewise, the sum from 0 to infinity of mu over 2 to the power of n is 1 over 1 minus mu over 2, which is 2 over 2 minus mu. Okay, so summing these up, we end up with the sum from 0 to infinity of fn over 2 to the n plus 1 equals a over 2 times 2 over 2 minus lambda minus a over 2 times 2 over 2 minus mu. Now I would substitute in our values for lambda and mu. So what does that give us? That gives us, so we're going to have an a, the 2's cancel, we're left with 1 over 2 minus lambda. Well, lambda here is 1 plus the square root of 5 over 2. Hopefully you can still see that. Minus a times 1 over 2 minus mu. Well, mu is 1 minus root 5 over 2. Like that. Simplifying this, we end up with a times 1 over, so we're going to end up with a 4 minus 1, that's a 3 minus root 5 over 2, minus a times 1 over 4 minus 1, that's a 3, this time it's plus root 5 over 2. Okay, so we're going to end up with a times 2 over 3 minus root 5 minus a over 2 minus a times 2 over 3 plus root 5. We want to add these together, so what do we end up with? We end up with a times 2 times 3 plus root 5 over, so if you multiply top and bottom by 3 plus root 5, you end up with 9 on the denominator. Similarly, we're going to multiply top and bottom by 3 minus root 5, and so we end up with 2 lots of 3 minus root 5 over 9. Oh, sorry, not over 9, over 4, because it's 3 squared minus 5. My mistake. And so we end up with, so we're going to end up with 2 times 3a plus 2a root 5 minus 2 times 3a plus 2a root 5 all over 4. So that becomes 4a root 5 over 4, which is a root 5. A, if you remember from sort of near the beginning of the question, we found that a was 1 over root 5. And so substituting this in, we end up with 1 over root 5 times root 5, which equals 1. Okay? And so this infinite sum of the nth Fibonacci number over 2 to the n plus 1 equals 1. Okay? So that is the whole question. It's a long question, I think, right? Like, this took me quite a while to do. It's not particularly easy either. So this is perhaps one of the more difficult questions. Hopefully I've explained it well enough. And good luck.